All right, so today we're going to be talking about radiation, or essentially radioactive compounds and all that, radioactive atoms. Okay, and so before we talked about isotopes, and again, when we talk about any type of atom, it's going to have a set number of protons, and again, protons are going to be that part, the positively charged substance in the nucleus of an atom. And again, we see that electrons can be interchanged, but we can also see that there could be a different number of neutrons, and when the number of neutrons isn't the same as the number of protons, again, we talk about isotopes. Today, we're going to figure out, or we're going to talk about why, with a certain amount of neutrons added to the nucleus of a certain atom, why that's going to turn it radioactive, and why that's going to essentially cause for that atom to be radioactive. Okay? And so we talk about unstable nuclei. And again, when a atom is unstable, again, when we talk about the different amount of nucleus, it's going to want to lose that energy. It's going to commence some type of radioactive decay. And so, again, we talk about chemical reactions changing the identity of an atom. No, we don't see that because you don't mess with that nucleus. But we see that the nucleus is affected by the different reactions. Again, we talk about that radioactive decay that will change or mess with the nucleus. Again, it's not going to change the identity, but it is going to alter how the nucleus looks and all that. Again, you're not going to see protons change in it, right? Because we have that atomic number. But what we see is that the number of neutrons could change. And through radioactive decay, that's how we see it change. So we see that they change because you want to see the atoms are trying to be stable. Just like with anything, just like with compounds, what we see is that they want to be stable. They don't want to be unstable. And so unstable systems, like atoms with the wrong number of neutrons and all that, are going to want to gain stability. They're going to want to gain stability by essentially losing energy. So the example is if you have a pencil standing on its tip, right? It's not stable. It's going to be moving around. It's not going to stay balanced. And so what's going to happen is the pencil's going to fall over. It's going to lose energy when it falls. Once it loses its energy, it's going to gain that stability while resting on the table. And the same thing goes with these atoms. They're going to gain that stability, lose that instability by losing energy. And so we talk about one example would be carbon 14. Again, when we talk about carbon, we know that carbon is going to have 12 protons. 12 protons. When it's carbon 14, that's telling us that there's going to be 14 neutrons. So we see that it's going to be not stable. Okay, it's going to be unstable. So what we see is that there's going to be some type of energy loss. It's not so much radioactive as in harmful, but what we see is that radioactive is going to try to shed those neutrons. It's going to try to lose that. It's going to lose that instability or it being unstable. But we use carbon 14 in a very productive way. We use it in carbon dating. So essentially what carbon dating is we try to figure out the age of different fossils that we find. Now, obviously, we don't have the technology to travel back in time to figure out when this certain fossil lived, what different time period. But there was a way, or there is a way now, in which we can figure out the certain date for a certain fossil that we find. And the thing is called carbon dating or carbon 14 dating. And what happens is that since the carbon is unstable, it's going to, again, try to lose that energy. And with that energy, that carbon 14 is going to disappear. And so it doesn't go away immediately. There's a certain rate in which it's going to disappear from. Scientists have figured out the rate in which carbon 14 essentially goes through its radioactive nature in which it depletes. And so, using that formula, they can look at any type of fossil or any type of older object that they find, and with the amount of carbon 14 that they have in that fossil, they can determine the age of it by using the rate or the equation that they have originally discovered. So, they find out that essentially they call it the half life because I believe uh, I think it's 5,260 years, you're going to see that half the carbon 14 are going to be depleted, or the quarter. And so, with that, all they have to do is essentially find how much carbon 14 is left in that fossil, and they can determine the age of it. They don't have to get their time machine and travel back to the time when it was alive. And so when we look at the type of radioactive decay, there's going to be a lot of different types of radioactive decay. The first one's going to be an alpha decay. And so, for example, when we look at helium, we see that it's going to originally contain uh, two protons and two neutrons. Okay, but what we see is that the mass number drops by 4, and you're going to see the atomic number is going to drop by 2. And so, what you're going to see is that the charge that we see with helium is going to be a +2 charge. And so, when we look at this chemical reaction here, we see that the atomic mass is 226. The atomic number is going to be 88, again, the number of protons. And so when we have these two combined, we're going to see that that atomic number is going to drop, that atomic mass is going to drop. What we see with a beta decay, so again, alpha, we see that both protons and neutrons drop here. With a beta decay, or the atomic numbers, sorry, not protons. What we see with the beta decay is that the mass number is going to stay the same, but the atomic number is going to increase by 1. So again, there's going to be a -1 charge, which is going to be the same as an electron. Okay, so if we look here, we have this carbon, it's going to increase its atomic number. So again, if we look at this nitrogen here, we see that the atomic mass is going to stay the same, but the atomic number is going to increase. So if we're looking at this decay here, again, it's going to be whatever nitrogen we see here added with an electron or that -1 charge. A gamma decay is when we see that there's going to be no charge. So no change in the mass number or atomic number. Usually this is going to accompany alpha or beta decay here. So again, most of the energy lost in radioactive decay is from the gamma decay. So again, we see here that with this alpha decay that we have this gamma decay noted here. And so when we differentiate between the types of radiation that we see, is that through the sled block, through whatever radioactive source we have, we can determine what type of radiation because of where the different particles lead to. Again, when we talk about magnetism and all that, we know that with magnets, opposites are going to attract. And so what we see here is that the negative charged beta particles are going to want to go towards that positive side. But we see with the alpha particles, so we see with that positive charge, they're going to want to go to that negative plate. So we're going to see that the particles are going to shift over to that negative plate. Again, and when we talk about a gamma ray, there's going to be no charge because it's not going to want to go to either the positive plate or the negative charge plate. So again, it's going to have a straight shot. And so when we balance a nuclear reaction, what we have to see is that the mass number and the atomic number have to be the same on both sides, so the same number. So when we take a look at here, the atomic number for, I believe this is uranium, is 238. We see here that the atomic number is 92. So we look at the product side of this, we see that this number is going to be 234. This atomic number, this atomic mass or mass number is 234. This atomic number is going to be 90. We know that in order for this side to be the same number as this side, there needs to be two more added to the atomic number, and we need four more added to the mass number. So again, each side is going to have a total of 238. So each side, let's see if this works. This side is going to have 238, and this side is going to have 238, so the mass number is the same, and the atomic number is going to be the same on both sides. Again, this is 92, and this is 92 also. So again, what happens when we see this nuclear chain reaction? What we see is that fission is going to occur. And so with fission, this is when the nuclei of certain isotopes are bombarded with neutrons. And so the nuclei are going to split into smaller fragments. So what we see here is that this uranium is going to come in contact with this atom here. And so through this energy, you're going to see that the neutrons are going to split up into smaller fragments. And see here that the neutrons are split up, and you have krypton here and the barium here. And so again, in that chain reaction, some of that emitted neutrons are going to react with other fissionable atoms, and which are going to emit those neutrons that react with still more fissionable atoms. And so how does fission and fusion reaction differ? So what we see with fusion is that small nuclei are going to combine and release much more energy than with fission. So again, more energy involved with fusion instead of fission. So again, with fusion, what we see here is that after the neutrons are going to interact, what we see is that the reactions are going to only occur at very high temperatures, in excess of 40 million degrees Celsius. And so again, I'm going to attach some videos with fission versus fusion so that you guys have a better understanding of what that looks like. But that is radioactive decay and how that looks with isotopes. So again, we talk about alpha, beta, and gamma.